we said. Right? But we showed last time that while the sign is sufficient to define the sense of forces for the axial and shear force, in the case of bending moment, if I just tell you that the bending moment is minus 120 kilonewtons per meter, you do not know in which direction it acts unless I tell you from which side I look at the beam or column, right? So that's what we said. So we said there is a little bit of a weak point there, and therefore we said that we plan to we plan to have an agreement that we are going to show the bending moments in a way that uniquely tell us which side is under tension, which is under compression. And we are going to do that by plotting the moment diagram always on the tensile side. So it means that if I have a beam, if I have a frame, and if I have plotted that the moment diagram, for example, is something like this, we said, for example, if I plot the moment diagram, the way I've plotted the moment diagram, without telling you whether I call this positive or negative, you know that in this side, the inside of the beam of the column is under tension. Here the outside, here the top, here the bottom, the top, the outside. Okay, so you fully know which is the side under tension. This is what we want to achieve. Okay, so we will not pay attention to the actual sign. I don't care if we call this here minus 130 or if I call it plus 130, right? What I care is the fact that I plot on this side. If I plot on this side, it means that if I was plotting the beam in such a way, if I was looking at the beam in such a way, if I got the number plus 130, if I looked at this in this way, since I plot on the bottom side, it means the bottom side is under tension, so this is what I would have gotten. If I would have looked at it from this side, and it is indeed the top side of the beam now is under thing, then my number would be minus 130. So depending how I look at the beam, that number will be either plus 130 or minus 130. But once you know what the moment diagram looks like, you can tell me also, if you tell me the sign, you tell me from which side you looked at it. For example, if I tell you that this number was plus 60, did I look at it this way, or did I look also? Did I look at it from this way? This is A, or did I look at it from this way? This is B. If the number is plus 60, which way did I look at the beam? A or B? Let's say this is the actual moment diagram. Correctly plotted. It means which side is under tension? This side or this side? The right side, right? So clearly, we're talking about a beam where this side is under tension, right? This is the side under tension. It means if the number is positive, it means the bottom side was under tension. It means we're looking at the beam from this way. That's why I called it positive. If I would have looked at it from this side, this number should be minus 60. All right? Okay. Now, I'll show you I will go over very quickly the main rules that govern the construction of the diagrams. I don't see some of the foreign students here, and I'm mostly worried about them. Actually, that's one reason why I'm doing all this. Not all of them are here, as far as I see. Okay. So, anyways, if it's your friend, please let them know about this. Okay. So, because they will have difficulty really to do things fast as we want to do. All right. So, the main rules that govern the constructions of the different diagrams. Okay. For the axial diagram and for the shear diagram, the rules are very similar. Okay, they're very similar. What are the rules? The rules are, first, if we see some concentrated load, we jump in the diagram. And if we see some distributed load, our diagram gradually changes. Okay? In which direction do we jump? All right, is the question. So it is easier to visualize in the case of V. So I'll start with V, and I will go later to N. So in the case of beam, where we have some concentrated load, let's say in this direction, then our shear diagram if we had a shear diagram, let's say the shear diagram was here at this value, whenever I see this load, I get pushed by the load in the same direction as the load. So if this was 100, and this was, let's say, minus 30 here, this will be minus 130. I will be moving according to the load that I see. Okay, if the load pushes me down, I have a jump. Whenever we have a concentrated load, we jump in the diagram. This is the important direction. In the shear diagram, it's very easy to decide if we move upwards or downwards, because we simply look in which direction the load pushes. If it pushes downward, we jump downward. If it pushes upward, we move upward. All right? This is very easy to prove, because when I have a concentrated load here, P, right? I mean, you need to know what is the proof in case you forget. If you had a shear here, if the shear here, let's say it was positive shear, let's say the shear